dare take a few minutes?
Yes, a few minutes will be fine.
I'm going to speak right now. There's actually an overarching issue here, which is the effect of science fiction on our beliefs about life in outer space. Most of what the general public and even the scientific world thinks about aliens, they've learned not from textbooks, but from movies and television programs. And they've seen Star Trek, where you can dial up Scotty and say warp 7, and that's what it takes to do a commercial for another star. And the belief is widespread because of this, that a few hundred years from now, that'll be true. That'll be the way it works. And that going from one star to another is very easy, and the technology is reliable, and there's a lot of it in action in space. And the fact is that that is not true. The universe is a huge and awesome place. It's full of hazards, and what's needed here, as they would understand the Fermi paradox, is a honest understanding of the challenges of interstellar space travel. And that's what I'm going to get to. First, hazards of interstellar space travel. People blithely talk about going at half the speed of light, spacecraft, things like that. First, we have no propulsion systems that can make that possible, but there are ones on the drawing board that might. They do involve very exotic technologies like controlled nuclear fusion on board spacecraft to provide enough energy for such high speeds. But what has been missed in this particular thing is that going faster than a fairly reasonable speed is so hazardous that you would not do it with living creatures. Now, how does that come about? It's because when you go fast, in particular a fraction of the speed of light, if you impact a very small thing, the amount of energy released is catastrophic. And just let me give you a feel for that. It works out very simply that if you're going about 12% the speed of light, and you collide with something, the energy released is mv squared over 2, high school physics, kinetic energy. mv squared over 2 at 12% the speed of light gives an energy release which is equal to that which is produced in the sun in the nuclear fusion process. In other words, a hydrogen bomb is created. And all it takes is a pebble the size of a BB striking you at 12% the speed of light, and you will be destroyed by a hydrogen bomb. Well, space is full of pebbles that have been thrown out of asteroid impacts and planetary systems and the like. And so what this says is you can't go fast. It's too dangerous. Well, how fast can you go? Well, let's imagine a tenth the speed of light. That's already very good speed. What's implied by that? Let's just imagine. Now I'm going to give you my solution to the Fermi paradox. Why the ticket is too expensive. 1/10 the speed of light. Let's just imagine. All right, you're sending a group of people that's enough to colonize another world, which is normally what's involved in the Fermi paradox, to create a colony on some other planet. We're going to go to 1/10 the speed of light. The nearest habitable planets are probably 10 light years away. This trip's going to take 100 years. We'll get back to that. That's probably not very inviting. But the main question, and this is just basic physics and what has been missing, and I reference it in any of the science fiction material, is how much energy is required to do this. Let's imagine your spacecraft weighs about the same as a very small airliner, a 737 aircraft. Most of you have traveled on one of those. And with a 737, you can take probably 50 people with some adequate supplies and means for recycling air and water and all that, which you would have to do on a 100-year mission. So 50 humans, that might be enough for a viable colony, although it's pretty commercial. It is a 737 aircraft, going 1/10 the speed of light. We'll take the mass of a 737 and just do the mv squared over 2 again. How much energy is that? Well, it turns out, I won't give you the number because it's one of those astronomical numbers that the astronomers tend to understand. The number is an amount of energy equal to 200 years of total electric power production in the United States at the present time. you would have to shut down America for 200 years to launch this mission. This mission, which is very hazardous, and it's worse than that. That is assuming that the energy conversion is 100% between the electrical power and the speed of the spacecraft, and no propulsion systems are that efficient. So it's going to be much more than 200 years worth. And worse than that only gets you there. It doesn't slow you down. You have no way of landing anywhere, and it doesn't get you back home either. So we're talking about prodigious amounts of energy here, and this is just basic physics, and there's no technology that can reduce the amount of required energy. Well, think about it. Would you like to take such a trip? Would you like to spend 100 years on a 737 eating airline food? Nowadays that means snack boxes, pretzels, occasional glass of water, recycled water, it's not very tasty. You're watching the same movies over and over. And just think what the price of the ticket will be. You have to pay for, each passenger has to pay for perhaps 10 years worth of electrical power production in the United States. Even Bill Gates would pale in the challenge to his pocketbook. So these are the reasons I think that we are not having tourists. Why interstellar space travel with creatures is very unlikely. I mean, the only solution, the only workaround of what I've just described is to go slowly. And then people hypothesize that maybe there's a suspended animation and things like that. But it's just not worth it. It's too costly, it's too hazardous. The chance that the mission will ever get there is very small because of the danger of collisions. And when you think about it, you do much better by learning about other civilizations.